This isn't a heating massage pen. Neither is it a device for my jaw pain. What I'm building is a reflection of myself, my story as an engineer and product designer. It's the proof I need that out of nothing, relying only on my own skill, I can create something another person will one day take for granted.
Let's get back to some real engineering this episode.
If you remember, the last thing we left off with is ordering our third PCB after a ton of debugging and design changes. Well, they've arrived. While that gets soldered up, remember how we redesigned the aluminum heating tip? Well, the new sample has just come in. Come on now, that's absolutely spanking.
And once again, this feels fire on the jaw. I've also made some changes to the casing since episode 2.
I no longer like the idea of using custom button caps like my original plan. They're just so hard to put in, and at scale that's just not going to work. Instead, I'm going to use the thin material for seeing the indicator lights as a compliant button type thing. So the case cap itself is going to be clickable. I'm really happy with how it works.
Okay, admittedly it looks way worse, but I think I have a solution for that we'll go into a little later. Okay, back to the PCB. Now that we've got it all soldered up, let's go and program it with the new pogo pin programmer that we designed in.
Yo, that's so much better.
Let's test that shit out.
First, I had to solder up the new 12-volt 40-watt cartridge heater that I designed to run off just the battery voltage. I've never prayed harder that I didn't make a stupid mistake here.
This is actually like gambling. I've never been so nervous in my life.
Absolutely unbelievable. It worked pretty much first try. Every other board I had to spend like a week debugging.
Alright, first time we can actually put this bad boy together. By the way, the reason it's splayed out like this is because I had to tape the battery leads together and it's pushing apart the walls. I know it's not safe, but my battery welder broke and I ain't gonna wait for a new one.
Not bad at all.
Alright, so here's the deal. I'm very happy with the PCB functionally working out, and I love having something put together, great weight. But we've got some problems to solve. First, there's the light leakage. I think the LEDs are a bit too bright and make it feel a little cheap. So I think I'm just going to add them to the PWM cycle and code to lower the brightness, as well as adding some barriers to prevent leakage between the red and the blue circle. But the elephant in the room for me is the heating. So as you know, the FDA does not take kindly to medical devices burning people. This is exactly why we put in current sensing into the newest circuit board. But I kind of just thought that this would be an extra safety feature that we would just be able to dial in later. And for now, we could just tune the PWM pulse width for heating to get the equilibrium temperature that we want. And that's exactly what we did for the test you just saw. But unfortunately, I really underestimated the heat dissipation that would come from the tip, which in hindsight is really stupid because as a heat conductor, aluminum would obviously just dump all of its heat into whatever surface it's touching, which in this case is your skin. So I realized that even if the massager gets to the right temperature, it almost instantly drops as soon as you actually start using it. There is also the case of heat up time, which is super slow if you're working off temperature equilibrium with PWM. And I can't think of any hard-coded methods that don't also have the risk of the user burning themselves accidentally. This is why temperature sensing has just become a top priority for me. So we have to go check that the current sensing method that we implemented actually works to estimate temperature.
So here's the plan. We've got the shunt resistor right here, and we're going to measure the voltage across it with the digital multimeter to find out what voltages we should be measuring on the microcontroller, or whether we'll even be able to detect any changes at all. At the same time, we'll be measuring the temperature. Okay. So here are the results from the test. Basically, as predicted, nichrome has too low of a heat coefficient of resistivity, which means the shunt voltage difference we end up measuring is way too small. The other problem is that since we're running the heater off the battery voltage directly, As it runs, the battery voltage decreases.
That means that if we don't have an accurate enough model of low temperature shunt voltage versus battery voltage, we won't actually be able to measure the current relative to what it would have been if it was a different temperature at a different battery voltage. I know it sounds all kind of complicated, but basically all I mean is that all the errors that we get from measuring and the design itself will add up to be greater than the voltage difference that we're measuring in the first place. So our temperature estimations would just stink.
For the next PCB, I'm going to go with an NTC thermistor. NTC stands for negative temperature coefficient and just means that as temperature goes up, resistance of our thermistor goes down. So, put in a voltage divider and sprinkle in a little math, and you can spit out the temperature with really solid accuracy. I didn't want to do this before since I would just have to have extra wires that had to reach the tip in an already crammed casing, but now we don't really have a choice. I was also roasted on Reddit for not having electrostatic discharge protection on my board, because we interface with the outside world through the USB-C cable. My fix is just to add a TBS diode between the 5V and ground that breaks down and allows current to flow when ESD spikes occur. The other thing I gotta fix is that I've been placing vias on pads the whole time because it lets me get things so much tighter, but apparently that's not good if you want to mass produce since it wicks the solder off the pad and can create bad joints. But honestly, I'll just do that when I'm making a final production version and just plug the vias for now.
Back to the casing. Let's talk about what the FDA journey that we had last episode actually means for the design moving forward. The main thing is that the device needs to have a label on it. A label with the barcode, instructions, contact info, a universal device identification, and all the icons that go along with it. This is no doubt going to add some costs, but there are actually a few silver linings.
First off, the label can wrap around most of the device and cover up any surface imperfections or gaps and give it a nice finish. So, even if we end up 3D printing cases ourselves, it will come out smooth anyway. It also gives us more color, design, and user interface options, and solves most of our light leakage issues. Finally, we'd be able to add some sort of indication as to where the buttons are and what they do, which right now I think is a bit confusing.
So that'll be coming up soon, but for next episode, get ready for a little branding and marketing. See ya!